Hello and welcome to my YouTube channel. This video is part of operating systems video course and today's topic is scheduling queues. Topics covered in this video are scheduling queues, schedulers, and context switch. The objective of multiprogramming is to have some process running at all the times and thus to maximize CPU utilization. The objective of time sharing is to switch the CPU among processes so frequently that users can interact with each program while it is running. And to meet these objectives, the process scheduler select an available process for program execution on the CPU. For a single processor system, CPU is allocated to the process PI and other processes has to wait until the CPU is free and it can be rescheduled. As processes enter the system, they are put into a job queue, which consists of all the processes in the system. The processes that are residing in main memory and are ready and waiting to execute are kept on a list called the ready queue. This queue is generally stored as a linked list. A ready queue header contains pointers to the first and final PCBs in the list. Each PCB includes a pointer that points to the next PCB in the ready queue. As you can see in the image, each ready queue has the queue header, and the queue header is having two pointers, head and tail. Now the head pointers is pointing to the first process PCB, and the tail pointer is pointing to the last process PCB. The list of processes waiting for a particular IO device is called a device queue. A new process is initially put in the ready queue. It waits there until it is selected for execution or dispatched. Once the process is allocated the CPU and is executing, one of the several events could occur. The process could issue an IO request and then be placed in an IO queue. The process could create a new child process and waits for the child's termination. The process could be removed forcibly from the CPU as a result of an interrupt and be put back in the ready queue. In the first two cases, the process eventually switches from the waiting state to the ready state and is then put back in the ready queue. A process continues this cycle until it is terminated, at which time it is removed from all queues and has its PCBs and resources deallocated. Schedulers. A process migrates among the various scheduling queues throughout its lifetime. The operating system must select processes from queue in some fashion. Now, the selection of processes is carried out by the appropriate schedulers. In a batch system, more processes are submitted than it can be executed immediately. Now, these processes are kept into a masked storage device. As seen in the image, there is a job pool for later execution. The long-term scheduler or job scheduler selects processes from that job pool and it loads them into a memory for execution. And the short-term scheduler or CPU scheduler selects processes that are ready to execute and allocates the CPU to them. The long-term scheduler controls the degree of multiprogramming, the number of processes in memory. If the degree of multiprogramming is stable, then the average rate of process creation is equals to the average rate of process completion. Most processes can be described as either IO bound or CPU bound. An IO bound process is one that spends more of its time doing IO than it spends doing computations. A CPU bound process, in contrast, generates IO requests infrequently, using more of its time doing computations. It is important that the long-term scheduler select a good process mix of IO bound and CPU bound. Medium-term schedulers. On some systems, the long-term scheduler may be absent or minimal. For example, Unix and Microsoft Windows systems often have no long-term scheduler but simply put every new process in the memory for the short-term scheduler. Some operating systems, such as time sharing systems, may introduce an additional immediate level of scheduling, which is the medium term scheduler. Now, the key idea behind a medium term scheduler is that sometimes it can be advantageous to remove process from memory and later the process can be reintroduced into a memory and its execution can be continued where it left off. Context switch. When an interrupt occurs, the system needs to switch CPU to high priority process. Now, switching the CPU to another process requires performing a state save of the current process and a state restore of a different process. And this is known as context switch. Where a context switch occurs, the kernel saves the context of the old process in the PCB and load the saved context of the new process scheduled to run. Context switch time is pure overhead because the system does not do useful work while switching. As you can see in the image, the partially executed processes can be swept out because the CPU has to load high priority process and that is swept in. Thank you for watching this video. If you have any doubts or questions, please do comment and do not forget to subscribe my channel and hit the bell icon for latest updates. Thank you.